Hello everybody, welcome to another video session with CELUS. I am Zach Peterson and today we're going to be talking about all of the cool motor driver components that you can access inside your CELUS designs. Now if you know me, you know that I do a ton of design reviews, and one of the most common types of systems that gets submitted for a review is of course something with a motor driver. Motor driver integrated circuits are very common, and of course they are tailored for different applications. So what we are going to do in this video is look at 3 common applications that you can target with motor driver components inside CELUS. Let's hop into the CELUS app and check it out. Now to access motor control components inside CELUS, there are a couple things you can do. Of course, you can start building your own block diagram, and then you can ask the AI or resolve the project to then find out what are the possible motor controller components that will fit within your project. What you can also do is you can start from a template. You can use one of the templates inside CELUS, and you can then modify that template to meet your needs for your project. Now you can see here on screen that I have a template that I've pulled from the main page on celus.io, and it already has a motor control block assigned to it. You can see right here we have an option for motor drivers. And if I just hit right click and then select Kubo, we'll be able to see all of the different motor driver options that are going to work within this system. So you can see here, if we just scroll down, we have 10 different options. Some of these are your standard motor drivers. You have one here for a fan controller, and then you have one here for a haptic driver. So we're going to check out 3 of these components. We're going to check out the DA7282, we're going to check out the DRV10983, and then we're also going to check out the MAX 31760. So let's go ahead and jump right in to the DA7282. So when you select one of these Kubos inside CELUS, you'll see here a schematic with a bunch of components in it, and then you can see here you have ports to connect to other parts of your system. For this particular motor driver, we have an I2C interface, and then we have some general purpose inputs. And if we just take a look at the data sheet, we can see what the application is for this particular motor driver. The DA7282 is a motor driver for haptic applications, or it's a haptic driver. And this driver has a differential output. It has a number of different features on it that you can see here in this list. Here we have short circuit control. Here, as I mentioned, we have the differential PWM output drive. We have very low latency from wake up to standby. All really great features that we would need for a very small device that has a digital input and PWM control. Now, if we just go back over here to CELUS for a moment, and we click this little info box, we'll be able to get a sense of what the total footprint is going to be for this circuit if we decide to use it in a PCB. You can see here in the DA7282, if I just click on this component here, you can see that we have a preview of what the circuit looks like. You can see here that we have the QFN component. Looks like we have some external capacitors and resistors. We have our 2 FETs, and then we have a connector to connect to the motor that we want to drive with this circuit. Now, if you look at the footprint in the previous screen, you'll see that it is a QFN footprint. But if we just scroll down here, there is an option for another footprint, which is chip scale packaging, or a very small BGA. And you can see that right here in the pinout diagram. We do actually have an option for a BGA. So that's a really great option if you're going to build like a wearable device that you want to have haptic feedback on it. Those wearable devices can be very small, the circuit boards on them are very small, and you might not have room for a QFN component. These wafer scale, or these wafer level chip scale packages that you see here on the left, they come in this BGA footprint, and that BGA package is going to be much smaller than the equivalent QFN. So that really helps you reduce the form factor if you need it. Now, if we just go back over here to the schematic and take a look at the pins, we see here that we have one pin, which is the NIRQ pin. So what is the NIRQ pin? Well, let's take a look at the data sheet, and I always like to just Control F my way through some of these things in the data sheet. And if we just scroll through here and take a look, we can see that this is the interrupt request line. So this pin is actually an output to the microcontroller that you're going to use to control the haptic sequences that are driven with this motor driver. And this NIRQ line is connected to one of the inputs on your MCU, and it basically reports when there's a fault with the motor driver. This is also really great if you want to have a small form factor system. You don't have to build any of that fault detection circuitry yourself. It's integrated right there into the motor driver, and the motor driver just reports to your main system controller when you have a fault. Then your system controller can implement whatever logic you need to do in the event that there's a fault in your system. And then as far as driving haptic sequences, it's pretty simple. You can just use the I2C interface that you see here, or you can use these general purpose inputs, and you can set up whatever haptic sequences you want with this motor driver. Now, one of the great things about Renesys components is they do provide a lot of design and development resources if you want to use this component in your system. So if you go over here to the product webpage and click on the Design and Development tab, you will see quite a few resources that you can use to help you build your own system. You can see here that we have a haptics GUI, we have a development kit with a BOM, we have a motherboard with a BOM, and all of that can be used to help you set up your own system. We also have here under the Boards and Kits tab, we have some evaluation kits that are available, and that can also help you build and debug your own system with haptic driving. The next component that we're going to look at is the DRV10983 from Texas Instruments. You can see right here what this circuit looks like inside CELUS. You can see that this is a little bit of a larger IC, and you can see it has an external inductor and some large capacitors. But other than that, the circuit is pretty simple. If we just, again, click on this info box, we'll get an entire rundown of this circuit, and you can see here that we have an estimate of the footprint for this whole circuit. So you can see here in this image that the footprint is a bit larger. Of course, the integrated circuit itself is larger, but then we also have this large inductor here, and this inductor is the largest part of this circuit. So let's take a look at the data sheet and see what we can learn about this component. Now, this driver is for a 3-phase brushless DC motor driver. So this component has a higher input voltage range, and you can see here that it lists it as being sensorless. So what does that mean? Well, normally a lot of these motor drivers will have an external current sense resistor that they use like for current or power monitoring, but this one doesn't require an external sense resistor. It's all integrated into the driver component. Now, if we zoom in here and scroll down, you'll see here that the footprint is offset a little bit because this component requires 1.8 volt and 3.3 volt logic internally, but you don't have to supply that with an external supply. All of that regulation is built into this component. All you need to do is add some external capacitors, as you can see here in the application schematic. And then some of the other really useful features that we have here, for example, we have thermal shutdown protection, overcurrent protection. As I mentioned, those regulators are built in, and it already has a built-in 5-volt step-down regulator and some other features here that you can see in this list. Now, as you can see from the circuit here in CELUS, there is an I2C interface, but there are also these other 3 pins. We have a direction pin, we have an FG pin, and then we have a speed pin. So these pins are what you use to control the speed and the direction of the motor that you're driving with this component. So let's take a look again at the data sheet, and if you just go down here to page 12, you will see here in this paragraph that I'm highlighting on screen the description of these pins. So we have FG being a speed indicator output, my mistake, not an input, and that shows the frequency of the motor commutation. You have the direction pin, which just controls the direction of driving, and then the speed pin controls the amplitude of driving. Now, if we just scroll down a few more pages, you can see here what are the different control methods for speed. So as I mentioned, you're using the speed pin, but you have 2 methods that you can apply to the speed pin to then drive this motor. You have PWM input or you have analog input. So you really have the option here, and you can drive the speed pin with either input. And then of course your other option, as you can see here in this diagram, is the I2C interface. Overall, this is a pretty simple but pretty flexible motor driver that you can use with a standard microcontroller. And then if you wanted to do analog driving, you would just need to add a DAC to your system to then configure that pin with an analog signal. And last thing, let's take a look at the Texas Instruments product page. You can see here on the product page that, of course, they also offer a lot of resources that you can use to set up a system with this component. You can see here that we have some reference designs for different applications, and then if we go over here to the CAD symbols, we do have access to footprints. Here, if you go over to the hardware development side, you can see here that we have access to evaluation boards, and then of course we have some software development resources that you can use as well. Now, if we go back over here to CELUS, I do want to point out one of the components in this list, which is the TC78B009FTG. This is a bit of a more complex motor driver from Toshiba, and if you take a look at this Toshiba component, it's actually quite similar to this Texas Instruments component in terms of the features that it has available. So if you want to use this alternative component for three-phase PWM driving of a motor, you also have this Toshiba component available as well. The next component that I want to look at is the MAX 31760. This is of course a Maxim Instruments component, but they were recently purchased by Analog Devices, so now it's an Analog Devices component. Just taking a look here inside of the CELUS app, you can see that this is also a pretty simple motor driver, and you can see here we just need some external resistors and a capacitor to make this work. Actually, we need two capacitors. We need one here on the VDD pin as well. Hitting the info button, you can see here that we get an estimate of the total footprint of this component, and you can see here total footprint is pretty small, and we just have a header and some resistors and the capacitors, and then our integrated circuit that's doing all the driving. Now you can see here, if you read through this description, that this is a PWM fan controller. And if we just take a look at the data sheet and scroll down to the typical application circuit, you can see here from these pins we have two tachometers on this chip, and that allows us to do driving with two 4-wire fans. So this is a really good option for example, a compact computer or a compact power controller or something like that. Something that's going to generate a lot of heat and needs some airflow. This gives you two fans that you can use to do that. They're plus 5 volts or plus 12 volts driving fans, but you could probably do this with a lower voltage fan. You just need to check the specs on your fan. But in any case, you have two fans that you can use and two independent tachometers that you can use for speed monitoring. Now, one of the cool features on this chip is the fact that it has built-in temperature sensing. So if you take a look at this list of features, you can see here what the operating temperature range is, up to 125 degrees C, so it's going to be appropriate for example, industrial applications. And going down here and taking a look at this application circuit, you can see here where the temperature sensing is implemented. It's done right here on these DXP and DXN pins. So this chip is actually doing two types of temperature monitoring. It's doing local monitoring directly on the chip with an integrated temperature sensor. It's also doing temperature sensing from a remote sensor, which is hooked up to these DXP and DXN pins. So this would be like with a remote diode connected transistor or a thermal diode like you might see on a CPU or a GPU. Now this is really nice because not all fan controls have this. Some fan controls will force you to use, for example, an ADC and an external thermistor to read the temperature in a specific location, and then you would have your MCU read that temperature and then use that to modulate or control your fan driver to the correct speed so that you hit the correct temperature that you're targeting in your system. Now in this application circuit, there are two pins here that are really important. These are the alert pin and the shutdown pin. And you can see here in the feature section that they describe briefly what these pins do. So here you have an alert pin which is dedicated just for telling your system host when there's a temperature fault. So it's an output, you hook it up to your microcontroller, and then your microcontroller is going to know when there's an over temperature fault with your fan controller. The other pin is a dedicated shutdown pin. And the shutdown pin is nice because it can be used to assert other devices in your system and force them to shut down if there's an over temperature event in your fan controller. So having the shutdown pin on the fan controller is really useful because it won't take up another GPIO on your microcontroller, and you can use that for some other task. So there's one last pin that we haven't discussed, and that is the FFFS pin on the fan controller. So this is a multiplexed pin, and it will output a low state if a fan failure is detected. Now remember, this is a failure with the fan. It doesn't necessarily mean that there is an over temperature event. It just means the fan has failed for some reason. The other thing that you can do with this is you can force this fan controller to run at full speed if you pull this pin low externally. So normally they recommend right here to pull it up to VDD with a pull-up resistor, but of course you can use it as you like. You could say, for example, toggle it down to low with a FET, for example. So a number of things that you can do with this pin. And finally, let's take a quick look at the manufacturer webpage to see what kind of resources they offer. You can see here under the software resources that they have made all of their driver source code open source. So you can go ahead and download all that from GitHub. You can also see that they have some software that they've provided for their evaluation kit, and they even offer an IBIS model. You don't see that very often for fan controllers or motor drivers, but they've made that available here in the resources section on the manufacturer page. So go check out those resources if you want to use this component. Thanks everyone for watching this video. I hope this shows you some of the very cool applications you can target with designs built in CELUS. Make sure to subscribe to the channel, make sure to sign up to use the CELUS app for free, and we'll see you in the next video.